Good morning, everyone. Very happy to share some of my knowledge and my journey in the space of LLMs for the last 2 years. It's been roughly 2 years it's been heating up. And wanted to, before I start on the presentation, a few years back, I did a hands-on session in one of the conferences on NLP, starting with bag of words, vectorization, classification models, etc. But now when I reflect, as I was preparing for the LLM Masterclass the last few days, I'm realizing the landscape of NLP has completely changed, right? So from bag of words to fine-tuned, handcrafted classifier models using language rules, etc. I think LLM has disrupted the space of NLP for the better, and any technology, I believe, the larger purpose of any technology is to democratize and get more participants in actively building the technology, right? So from that perspective, my experience so far has been with LLMs that one field that it has absolutely disrupted is on NLP. So we'll talk about, the way we will go through this is little bit of introduction to concepts, and then we'll see few case studies kind of application. So that's how we'll go about this session. I'll go to the first slide. Yeah. So we have been talking a lot on language models, and there's been media buzz on this. Everybody talks about language models. In fact, even when in celebrity interviews, people talk about language models, right? That's how much it has reached. But it is not like language models came in the last few months or last few years. It's been there for a long, long time. Very, very simple use of language models, and whatever you are seeing on the screen has been in production up to even, let's say, 2013-14. People have been using this as language models. So what is a language model? It just models patterns in a language, and then it tries to predict based on that. So if I say hi, how, and then you know the next word I'm going to say most likely is are, right? So that is a language, it just fundamentally predicts what could come after what. Then there are variations of it. You could predict it based on the last word, you could predict it based on the last 2 words, you could predict it based on the last 3 words, you could predict it based on the word after, and you could fill the word in between, right? So there are various combinations. Very, very simple way of language models are statistical language models. So on the screen, you see first word is hi, second word is how, then it could have are, is, do as the next probable words with certain set of probabilities. And how do you very simply compute probabilities? You take a corpus of data and then you just do frequency distribution of a word and its next word. Then you get your language model. That's your basic language models. It may sound very, very basic given the whole possibilities that LLMs have presented to us today, but this was in systems working and could work even today for a lot of use cases. And that's how we think about languages, isn't it? If somebody is talking about few things, then you know what the person is talking next about. And if you think on our phones, where you are typing something, it is prompting the next word, it's fundamentally based on this. So this is where the world was. A lot of applications running on this simple statistical language models, possibly a few years back, and maybe few applications running on this even now. So we'll go to the next slide. Now the problem with this is, it's very word specific, right? It does not understand meanings of the word, so to say, right? It's every word needs to have enough representation in the corpus for you to predict a probability. So if it's a rare word, let's say we are talking about different trucks, cars, and trains in the same thing, each of these should have enough representation in the corpus for you to make a probabilistic prediction on top of it, right? Suppose if it's a new word that the corpus has not seen, or if the word is not very well represented, suddenly we are talking about heavy commercial vehicles. HCV is coming in, and that is not represented in the corpus about vehicles, the language model will suffer. So we get into something called as word embeddings. This is also a process of converting words to numbers, but in related spaces. So this is a very simple projection of what word embeddings could mean. So for example, it says cat and dogs are similar, whereas it's very different from apple and it is very different from car, right? So it's this way you could look at related words as the next word prediction. You could also look at rare words. You could also on the go give it prompt, and it can also say, okay, this is pretty much nearby to the knowledge I know. So word embeddings did few things. It did expand the scope of the vocabulary, which was very restrictive in the statistical language model case, right? So it only knew the word it saw in the earlier example. Here it could also project it to words that it is not in that corpus, but it has worldly knowledge through which it can learn something. It could also model this for rarer words, and which is very common, right? When we speak, not all the words could be in that corpus that you have trained. There are always words occurring outside, especially in things like your nouns and class of entities. This kind of problems keeps coming in. Very, very common in real world applications, where let's say you are building a chatbot for a vehicle company, or whether you are building it for a bank, etc. There are a lot of entities which are not always trainable. So you want the model to learn either through extension of knowledge or through certain representation which have closer meanings together. That's why embeddings is very important, and from embeddings came, let's go to the next slide, the neural language model. So what happened was the statistical models were very flat, right? So you took the words, you saw what is the next distribution, and that's about it. And that you could do only so much, right? The generation will not be sophisticated, it will be very restrictive. It could have only unigram, bigram kind of generation. Whereas the neural language models kind of took it to another level, where it can generate, where it can predict things that is very sparse in the vocabulary also, and by using word embedding. So each of these words, for example, hi, how, etc., will have a number representation that goes into a neural network, and then it predicts what are the next possible words for this. So this is where language models were largely used, at least a few years back. A lot of these were LSTMs, or they were RNNs as the core unit of the neural network. From here we come to, go to the next one, transformers, right? So there is this paper which many people speak about. It's all about attention. So that kind of changed the landscape of the neural language models. So instead of each of the cells in the network have being RNN or LSTM, etc., became something called as a transformer, right? And at the core of a transformer looks at a layer called attention. We will see what attention solves, right? Just look at this. Washington in Washington, DC, or George Washington. Let's say stick is a word, and it says, let's stick together to the old man uses a stick. Or the third example, the animal didn't cross the street because it was too tired. In all of this, the same word has different meanings. While we talked about word embeddings, we saw that they are words that we have not seen, and they are words that are similar, right? That we wanted to group them together. Here, it is the same word, but has different meaning and different connotation also. If you see the last one, it says, the animal didn't cross the street because it was too tired. We don't know whether it refers to the animal or it refers to the road, right? So how does a language model understand it? That's when attention played an important role. Now, how do you understand it is, you project all of these words to the other words that is following in the sentence. So that's how attention works in a very intuitive way. For example, the weight of the word with respect to animal and the weight of the word of it with respect to road, it learns automatically that it has a higher weight on animal and instead of the road, and that's how the language model gets a lot more intelligent. So this was the concept of attention, where a word association with other words in the sentences are learned while training it, and hence it's much, much more intelligent than all the counterparts it was. And once attention got fixed, a lot of improvements and enhancements in the space of language models, which contributes to generation, took place. So we'll go to the next slide. I'll come back to tokens, so we'll go to the next one and then we'll go back to tokens. Yeah. So this is how our GPT architecture looks, and the attention and feed forward, that is a block that gets trained, and many such blocks, many such transformer blocks together combines into a language model architecture, and what you're seeing is a very, very simplistic representation of a GPT architecture. So at that, the input is your word. It gets tokenized into smaller chunks of, input is your sentence and it gets chunked into smaller set of tokens. That goes into the embedding layer we spoke about. There is also positional encoding, which kind of encodes the sequence of the words that is there, and then the transformer blocks kicks in, right? We'll go back to the previous slide now. On the tokens, I want to take few minutes and explain it, right? What is a token? At simple, for example, on the right side, I am Mathangi, I am here to talk, right? That's a sentence. So the machine should understand it. For that, we have to decompose the sentence into set of tokens, into set of a group of characters, right? So if at the core, you could just split it as a word. This is the simplest way of creating tokens. But this will, let's say if I have put a smiley or something at the end of it, this wouldn't have been able to capture. But if you see some of the advanced tokenization into the LLM models today, it even captures the smiley out there. So you can see this is llama, and you could see that the smiley also has certain token representation. So, from whatever experiments we have done, seeing that llama as tokenizer can encapsulate a lot more than even GPT 3.5 on this. So this is how it gets represented. So when people talk about, hey, this is my context window, beyond this you cannot pass a context to the LLM, your prompts have to be shorter. The crux of it is the tokens. And how it takes all your prompts into tokens gets into the context windows. So we'll go into the applications now. Next slide, please. Next, yeah. So before we get to applications, another one common thing that all of you might have heard and using is LangChain. So this is a framework which will help you take up any LLM and then construct an entire application on top of it. So LangChain is fundamentally a framework which consists of memory, chains, agents, and external data. It will help you build your LLM applications using some of these components, plug and play, and then out there you can build a quick LLM application. So for example, memory is remembering conversations. So all of you would have played with ChatGPT. If you start a session, it keeps remembering whatever was your history, right? So that's memory. Chains is you could produce a generation. On top of the generation, you want to do another generation. On top of it, you want to do another generation. Or on top of it, you want to do another task. So list of actions that you want, list of generation plus actions that you want to do could be combined into chains. Agents are basically, you want to give certain part of your task to certain agents and certain part of your task to some agents. Some agents specialize, let's say, in writing SQL queries. Some agents specialize in getting knowledge derived from Wikipedia, etc. And external data is the ability, more than what the LLM has, but you want to refer it to a source and you want to fetch some information from there. That's where the external data comes in. All of that is part of the LangChain architecture. So you take an LLM, apply it on a LangChain architecture, use it to do a bunch of tasks, and that's how LLM applications can be built very fast, right? We'll go to the next. So we will start with a few short prompt, and we will go through certain case studies on this. The difference between when few short prompts, I think, actually made a huge difference to what LLM's applications were. Not only does it generate to what you say, but then it also can learn on the go, on samples, and then generate much more meaningful context. So this is just a prompt. So we are just trying to get an SMS marketing for user to come to a retail store, right? So that's the prompt. You need to come, we are just telling what is the role it is going to play. And the tone, language, and query is part of the LangChain prompt templates, where we are going to pass these variations, right? The query is the instructions. Tone is how do you want the SMS to change? It should be casual, or it should be formal, how it should be, etc. And then different languages it can generate. And this is GPT-4o and was trying with a bunch of Indian languages. It has further instructions on when it should be translated in that language, etc. And then some more instructions here, right? And this is the set of a few short prompts where it will emulate based on the examples given. So you give the set of examples plus you give the instruction. That makes nothing but a few short prompts. So we'll go to the next slide. So I was just generating it for a bunch of tonality, excitement, factual, friendly, and then a bunch of languages. Then it just generated the SMSs. You can go to the next slide. Sorry. Yeah, so I don't know how much of this is readable, but this is exact output that I have shown from the Colab window. So you can see the first one is more exciting. Then there is also, it is stressing on the third one, if you see, it is stressing on the word free. You can also see how the sentence case, etc. is different across this. And you could also see a mix of transliterated words as well as Hindi words that is written in. Based on however the prompt examples are given, this is an example of how do you give examples plus how do you give the instruction to kind of get the output. You can play around, it's a lot of fun to play around with it. So you can put a lot of tones, you can put a lot of languages, you can give it a lot of instructions. And what we are seeing is the LLMs are kind of capable of handling a lot of regional languages also. I've just given examples in Hindi, but this works for Tamil, Telugu, and any of those languages, and it's pretty efficient and very realistic SMS. It's not, one of the things that I was worried while was doing this example is it could get very urbanized and it could get very, the SMS that's kind of in the West is what I thought it will follow a pattern. But once I specify, normally I specify things like do it in Indian English, then the example and the tone of the message and how it is written literally changes. Yeah, we'll go to the next one. Yeah, so before we go to the next slide on this, a few words on classifier. I was one of those heavy proponents at least a year back where I was thinking classifier is one area where generation will not pick it at all, and you can never beat a generation-based used classifier as compared to a discriminative classifier. So I think very slowly, but surely I'm getting proven wrong on this one. This is where we can use the classic NLU tasks of understanding what the sentence is and then what are the different topics in it, which used to have this entire structure starting from convert the words into numbers using bag of words, form a 𝗱𝗲𝗻𝗲 matrix, then do your, before the 𝗱𝗲𝗻𝗲, do your POS tags, do stemming, do punctuation and all of that. Then you get into a classifier and then fine tune and hyper tune the classifier. Right? This is how the entire process of classification was. And for anybody to get into for anybody to get into NLP, to build them a first good classifier, if they are academically trained, maybe it's and this is their first problem in the industry, it could take them anywhere between 3 to 6 months to crack it. That's how NLP was at a point in time, right? And the advancements in this field with LLMs coming in, it's possibly for somebody not to know anything about bag of words, not to know anything about how classifiers work, it is few prompts away to build a classifier today. That's what I'm going to show. I'm taking a problem of not so often touched problem on sarcasm detection. Even today, it's a huge area of research and everything. Not that this classifier did extremely well, but for just few lines, if you could get a classifier, it's magic out there. We'll go to the next slide. So this was the prompt on sarcasm detection. There's nothing fancy I've given, except that I gave it a lot of training samples, which had classified, trained supervised model. Unlike the few short examples we saw earlier, which had only few examples, I gave it quite a bit of samples. And what I found out is the more samples it gave, it was also kind of doing better. Of course, there could be questions on how much context window will you use and things like that. Those are there. Those could be at the restriction of using a full-fledged classifier. So this is, all you have to say is classify given sentence and then use outside knowledge. That think step by step is another area of prompting, which says it's more about chain of thought, but first see the words, and then there are some instructions on how it should classify on something being sarcastic or not sarcastic. The other part is don't classify if you don't know. If you don't know, just say don't know, which is 𝗃, it will return as unknown. And don't respond. So this is another thing. Don't respond with explanations. Only output the classifier. So there is no, that is where you're cutting out, so to say, the generation part. Of course, there are, because we talked about LangChain has better frameworks like Pydantic, which it will output a JSON output the way you want to give it, but could also be done through simple prompts like this. We'll go to the next one. So this is the output that I got. This is the classic sarcastic class data set that's out there. A lot of people have worked on it. It's a Kaggle data set. Anyone interested, go and try it, benchmark it with a classic classifier versus a generative AI model approach. There were some of the predictions were good. Some of this I thought I think there were ones that it marked as the GOP Stockholm syndrome, for example, it is marking as sarcastic, whereas the original data said it is not, but I think what the model was saying was good. And what I realized here was the more we train this, it's also kind of learning, the accuracy is kind of getting better and better. Of course, we didn't go through the article link. It was only a headline classification. If there had been also article link and that could be summarized and fed into it, there could be further improvements on this classifier. I would recommend this to use to problems which is like this, right? Like sentiment, sarcasm, where what that classification is a well-known concept, then it could also use outside knowledge. If it is going to be within group, it's a closed group classification. So another time I was trying a classification was to classify a given vehicle name into a commercial vehicle or a passenger vehicle. So let's say if it's Tata Nano, it should say passenger vehicle, and if it is, let us say Ashok Leyland, it should say it's a commercial vehicle, right? So that kind of closed group problem. There also, it was decently doing and possibly better than a classifier, because the LLMs will have higher knowledge even if it is trained, let's say, a year back, with the data till a year back, it will still do better, and then you add more context to it, it will do better than your classifier. So this area, I don't know, not many articles out there on classifiers, but I think certainly there will be more progress and more improvement that we can have while leveraging LLMs for classifier. One of the other ways to use this is also to generate a lot of samples, because that we don't have in many use cases. So you use the LLMs to generate the sample, then you classify it using an LLM, then you use the machine learning model to finally classify it. So that's another approach. We'll go to the next one. Okay, we are getting into another area called as retrieval augmented generation. Again, when LLMs came in, the first thing that the people said was, okay, this will work for what is the temperature, and generally chatty messages where you just want to have a chat with a bot, but not for very useful use cases, because context will not be known to the LLMs, and context is business use cases is all about context. RAG completely broke this thing, and of course, see, there are two ways to pass context. If you just think about and reflect at RAG, there are two ways to do it. RAG is, let's say there is a 50-page document, and then you want to make sure all your responses are coming from that 50-page document. If the context window is infinite, you could just pass the entire document as a context and then ask through prompt. But where there is a limitation on context window, and of course it costs, you kind of resort to RAG. And at very simple, this is what a RAG architecture is. So there is a model, there's an embedding model we talked about. There is an embedding model that's there, which we saw earlier. So let's say there's a 50-page document. That 50-page document gets converted into numbers, and the numbers get indexed into a database, right? So that becomes your dictionary. Then when a user asks a question, you retrieve the relevant part of the document from the database and then say this is my relevant area, and then LLMs use that relevant extracted information as the context and possibly the only context if you instruct the LLM to do so, and then gives a response. So this is the crux of RAG. And of course, there are nuances in it in terms of how do you convert the words into numbers, that's your embedding model, and then how do you retrieve it, how many do you retrieve, how do you index it, what is the indexing store that you can store this, and when the user asks a query, how do you kind of find the most similar set of words from the store, and then how do you scope it down through an LLM. So those are the moving parts here. And of course, huge area where people are constantly figuring out how do you find out the nearest neighbors, how do you retrieve, how do you chunk, all of that makes what RAG extremely interesting. And of course, there are articles out there which says RAG is dead and the next one is in. The thing about LLMs is before, at least I feel this, before I start coding the latest strategy, somebody has already written it is dead and the next one has come in, right? So the phase is, the world is moving so fast in this area, and that's possibly why it is also very exciting. Before we could figure out everything on prompts, somebody said prompting is dead, and then the automatic prompting kind of things started coming where prompting can be learned through supervised mechanisms, right? So but out there, these are techniques that's there. There is also an advancement on this on graph RAGs, where instead of a vector database which converts numbers and puts it in an index, you also have graph node representation, plain text graph node representation, and then from the graphs you retrieve it. So this is a small case study. Let's say there's a FAQ document. You may not be very, this is not a, just to be very clear on privacy and all of that, I didn't put any of the existing FAQ documents out there. I just generated the FAQ document. These are the FAQ documents, and let's say if a user wants to say how to block the card, what is the nearest branch, or how to activate the card, we should find a response from this document. This is a pretty simple, straightforward task. So these are the steps involved in it. There is a FAQ document which we saw, and then from there we are converting into strings, and after that there is something like once you extract the document, right? It's a PDF document, sometimes it can be images also, you extract the document, and after you have it in text format, then you want to now store the text. You want to divide the task into chunks. Let's say there is a document of, this document had some 5,000 characters, so maybe 1,000 characters, you chunk it, right? So that is, the chunking portion is what you're going to retrieve, and that becomes the context to the LLM. That's the relevance of chunking. And then you convert these chunked words into numbers. The numbers get indexed and saved in a store. I've used Phase for this, and the embedding is through ADA coming from ChatGPT. The GPT-4o. Then on the user query, again you have to convert the user query through the same embedding model that you converted your FAQ document. So same ADA is used. And then you do a distance similarity between the vector that has got retrieved from the FAQ document and the vector that has got retrieved from the user query, and then whichever is similar becomes your answer. Now pass the answer as the context to the LLM for you to get an answer. This is the crux of RAG, right? What people do is, at chunking, there are different strategies. It's another big area, like do you have to chunk it through characters? Do you have to do through fixed length? Do you have to do a recursive method? Do you have to do semantic chunking? Do you have to do sentence splitter, etc. on the chunking strategy? Then from there, different methods of embeddings are there. There are something that comes out of the box through the LLMs, and there are other embeddings that you can out there use and put it out. And then there are stores that just indexes and saves these numbers. These stores are different because some can be faster in retrieving it, etc. So there are different stores, different DBs in which these embeddings go in. Then there is also, how do you match distance? How do you match the user query to the user query's embedding to the document embedding? What are the different strategies you can use? What people also use in this process is, while the user query comes in, they generate on top of it. So if I ask how to block my card, they will generate 4 or 5 variations of it. How to block my card quickly, or how do I make sure nobody uses my card, I have a fraud, how to block my card, etc. Right? So those can be generated. These generated user queries are concatenated and again get an embedding, and then in order to make sure that the user queries have a match, you do all of this, right? So this is just an example of how to do a query expansion on top of a user query in order to match to the database that you have. And there are again very different strategies in making sure your retrieval works so that your language model answers from the retrieval. Now the whole point of it was, how do you make sure your LLMs don't hallucinate? How do you make sure that it only answers to your business context and it is not throwing something out there which is nothing relevant to your business? And RAG literally cracked that completely out there. So you don't need to write a lot of instructions. So if I have to instead write these instructions, then a lot of do not do's we have to write. That's another way to reduce hallucination. But in this case, with RAG, a lot of do not do's can really come down. I put the prompt here. So this is simple RAG. So that RAG, that out.bin you are seeing, that is the index file, and that is based out of the face store that I showed you. And make a payment is what the user is saying. What I am showing is the inner working here. That 674 is the indices it retrieved, and then it's saying, how do I make a payment on credit card? Don't look at the replacement card. That was the text before it in the FAQ document. So it returned this text chunk from what I was querying it to be. Now, then this is it, right? So now you see the prompt. Sorry, I can show. The prompt in this, I will just tell you. The prompt was pretty simple that I wrote on top of it, which says, look at only the retrieve query, don't do anything else, and then it just said whatever is the right part of the overall FAQ, right? It said, how do you make an online payment on top of it? So, and one of the things observed was, when I did not give, don't refer to anything outside of what is being passed to you, it was also generating its own answer. That's the hallucination bit. So it was saying, from its knowledge, how do you make an online payment? It was throwing it out in own channel. In this case, it was not even prominent for me because I generated the FAQ itself. So it was just giving a very relevant answer, except that the retriever was failing because of some bug. But reason I'm saying is, this is how you control, this is one of the biggest tools to control hallucinations, where you say you keep it only to the context passed, and then you pass the context through a retrieval text, right? So again, there is a lot of variations like we talked about, and another big variation is if context windows do become pretty large, which is the next phase of LLMs where it's going, then how people are going to use RAG, etc. Is questionable. But at this point in time, RAGs is the biggest tool to make sure it gives non-hallucinated contextual responses. So we are at top of the time, so like 10 minutes we have. Can I open for questions? Yeah. Are there any questions? Sorry, yeah, please go ahead.
So you said RAG using that you use vector DB to store all the. So in your use case, you said you're using RAG, and RAG is stored in vector database. How do you consider the number of embeddings that we need to actually add into the vector database? Because in some cases, your embeddings itself is so huge that the cost of vector database storage itself is very high. So
see, it's a trial and error, right? It's a compromise of it's few things here. One, the embeddings that you are creating is a direct result of how you have done chunking and your chunking window and overlap and all of that. That is an important thing. You chunk too granular, then you need, while it is retrieving, it has to retrieve more documents, etc. So chunking the number of items for retrieval should go hand in hand on this. Agreed on the cost aspect, so then you kind of play around a little bit with it in terms of do you chunk more, have a larger window, and hence you reduce the size of embedding, and hence your storage on vector DB and it reduces, or you chunk lesser so that you get the right retrieval of information, right? So that's how this works. And that whatever it retrieves also passes as a context window. There is a cost on that as well. So you play around and get it. Of course, you can try with open context. If it's a smaller document like what I showed, possibly the best way is to just give the entire thing to the LLM and say, without the RAG, do it. Some cases it does work. So I was trying this for resume extraction, right, which is generally 2 pages or something like that. There, without the RAG, it was doing far better because there is no information hidden from the LLM. It was directly everything got into it. Of course, then the context window costs. So you figure out the match on this.
Thank you.
In RAG, let's say, for example, you're parsing data from public domain, and there are multiple sources of information. There are conflicting informations, right? How do you weight the source of information to get the reliable output?
So there was another concept that's doing well called as LLM Judge. So what you do, and of course, see, all of this costs money. So I'm just taking that out, and we're seeing where some of these costs are going to come down, etc. When there are conflicting information, you could do a polling of multiple LLMs. Then you could get even if it is the same LLM, but you are asking the LLM to say whether the response you have done is correct or not. Do a rating of 0 to 5. Then maybe do multiple LLMs score that, and everybody gives a rating, and then you pick the most common one. Possible, yeah, this is just something that I could think on the go on this.
My question is, if you do this in real world, right, and you know, we are in a boardroom and we normally give a believability weightage based on the past history of that person's point of view. So how do you know the judge is believable?
That's where, see, in this case, the judge is in itself another LLM. Now, if you think that from that perspective, let us say, then you create an agent, let's say. Then we can move to agentic, and then there are a bunch of agents you create. Then you weight one agent's response more than the others. That's also possible.
Got it. Thank you.
See, sometimes you don't need to solve everything with it. You get the entire answers. Then you have a pre-weights that is assigned, and then you take it from there.
We can take next question. Any other questions if it is there?
One.
Is it okay if we take that like in the lounge session, like we are running a bit late, so
Sure.
would that be okay?
I think one question we'll take, and then we'll close with that. Yeah, go ahead.
Okay. So we have been using RAG for almost like 1.5 years now. Okay. And the problem is not with the RAG technology. The problem is the data which is fed into the RAG. So it's the traditional thing of garbage in, garbage out. Have you found out, or from your experience and implementations, have you found out a way of implementing a data observability framework in the RAG to make sure it works? That's question one. Question two is the chunk-based RAG also works fine, but is there a way that you recommend potentially without using a multi-agent framework which chunk to go and hit? So every time you implement a chunk-based RAG, it creates a separate vector DB, right? And the latency increases if you go across those multiple vector DBs, right? So these two questions. Thank you.
So what chunking strategy to use? Of course, there is trial and error, but then you could also ask an LLM on for this type of document, what could be a right chunking to go for it. That could be there. But on your other questions on garbage in and garbage out, your question is on how does it give a proper response, is it? So if you're again talking on the hallucination, see, somewhere we need to, at least this is my sense, I exactly don't know the problem, but where we are, and we have done this for some of the applications where we are using RAGs are summarizing annual reports of the companies, comparing two annual reports, comparing annual report with structured public data available from MCAs, etc., where you really cannot live with hallucinations and all of that. In that case, you do, like I said, you do an eval on top of whatever it is returning. Sometimes you also ask it to little bit expand on top of the retrieved content that it is coming in, not only use whatever is there in the retrieved content. Those could be there. See, it will boil down to either chunking better, or it will boil down to writing your prompts better, or it will have another LLM which is kind of looking at this LLM, or best case possibly is where you do some level of pre-processing on the data that is input so that the data is not, data contains some pre-processed information. An example is, let's say we are computing CAGR and things like that. Rather than, now it is working out, but the earlier LLMs we were trying was, we used to compute the ratio itself and then give it out for a summary. So some of those is what at least we have tried, and that's been my experience.